Generative AI changed what software can do. Models can write, summarize, translate, and reason over text as a general capability. Think of an LLM as a reusable intelligence layer. You wrap it with product logic, data access, and guardrails to build useful apps. LLMs are a subset of large foundation models. Foundation models are broadly pre-trained and can be adapted across many tasks. An LLM is a deep learning model trained to predict sequences of tokens, enabling many language tasks through the same core mechanism. Deep learning uses multi-layer neural networks to learn patterns from large datasets instead of handcrafted rules. Visual layered network sketch. Traditional ML often targets a single task with curated features. LLMs learn broad representations from massive text and generalize via prompting. Visual two columns comparison. Foundation models are trained once at scale, then reused and adapted. You build many downstream capabilities on top of one base. With large language models, natural language becomes a programming interface. You specify intent in prompts rather than implementing every rule manually. Many tasks, one model voiceover. A single LLM can perform multiple tasks: summarization, Q&A, classification, because it learned broad language patterns during pre-training. A prompt combines the instruction and relevant context. The model generates the most likely continuation given that input. The model estimates probabilities of next tokens conditioned on previous tokens. Prompts steer what next should mean. You can view prompting as adding evidence. The model updates token likelihoods based on what you provided, biasing outputs toward the goal. LLMs can't consume raw words directly. Text is converted into numeric representations that neural networks can process. At the core are neurons connected by weighted links. Training adjusts these weights to reduce error on the learning objective. Networks are organized in layers. Input receives data, hidden layers transform it, and output produces predictions such as next token probabilities. Tokenization breaks text into smaller units, words, subwords, or symbols, so the model can work with a fixed vocabulary. Everything, training, context length, and cost, is measured in tokens. The model's window is a maximum number of tokens it can attend to. Each token is mapped to a vector embedding, so meanings and relationships can be learned as geometry in vector space. In embedding space, semantically similar words tend to be near each other, helping the model infer meaning from context. Vector arithmetic can capture relationships like king minus man plus woman approximately equals queen, illustrating encoded structure in embeddings. Attention lets the model weigh which earlier tokens matter most for predicting the next token, improving understanding of context. In self-attention, tokens within the same sequence influence each other, so meaning is built from interactions, not isolated words. Training uses backpropagation, compute error, propagate gradients backward, and update weights so future predictions improve. An optimizer like stochastic gradient descent adjusts parameters using gradients, gradually lowering the loss over many iterations. LLM scale is about both parameter count and training data size. Bigger models typically need vastly more text to learn reliably.